before we start the sketch, I was looking at graphs of these. Does anybody, I remember in MHF, one of the things I recommended when we started, when we got into the curve sketching, was I strongly recommended you sketch, or like maybe with technology, a bunch of different curves, even if you're not asked to sketch it, but you're solving an equation or something like that. Now, I've mentioned it, I know, in this course as well, but just to get a sense of what different kinds of things these curves look like, because our goal is to be able to sketch new curves, different kinds of curves that we haven't seen before. And while we're doing all the work to determine the properties in order to sketch, we're trying to get all those properties so we can build a picture in our head of what this thing looks like, right? Where are the maxes, where are the mins, where are the points of inflection, where are the intercepts, all these different details, so that we can put them together and form the sketch, obviously, right? So the more you've looked at different kinds of graphs, either in a textbook or on a worksheet, if there's just different examples of graphs, or you graph them yourself with technology or something along those lines, the more you get a sense of what they look like, I think it's just easier to then visualize these things. So here's one. This is similar to one that we're going to do. I don't know that you've done one quite like this before, but I thought it was really interesting how many points of inflection this thing has. It's obviously, it's not repeating, it's not periodic in the same sense of sign, but there's some kind of pattern where it's going up and down and up, but it is going up forever, right? So it's not periodic, but so here's how I would look at this. I'd say, well, it's concave down here, concave up here. That looks like it's concave down. That's concave up again. That's concave down again. Concave up, concave down, concave up. Like, that means just in this section here, there must be a point of inflection in here somewhere, in here, and in here. Like, there's 3. That's a lot. And so if I was sketching this, all of those points of inflection would have to come out in the second derivative set it equal to 0. Like, you'd have a whole bunch. Okay, which would maybe be strange. So like this may not, that I don't even know what that, I don't remember what the equation for this is, but it may not be one that we could solve for, because we have to be able to solve when we set the first derivative and the second derivative equal to 0. Those have to be solvable. But there can be lots. And it's just interesting how when you look carefully at the concave up, concave down, you see it switching back and forth a whole bunch of times in there. Something to think about. Let's take a look at this. This is our last day of sketching. We're going to do a little bit more practicing sketching along the way in the review and different things, but this is our last day on actual sketching. And hopefully we're getting a good sense of how these things go now. And the criteria for sketching is going to be the endpoints, so where it starts and where it ends, the intercepts, the critical values, max mins, local extrema, whatever you want to call them. It's kind of all the same thing. And points of inflection and concavity, intervals of concavity. That's the criteria, meaning those are all the things that you have to do, right? You have to do a fully labeled graph, including all of those details. That's what we mean by sketch in this case. Asymptotes too, but there's no asymptotes in these functions, typically. And so hopefully you kind of know what that means. You know the order in which we do it and the kinds of things we have to do along the way to get all of those things. We'll start with the intercepts. The Y-intercept just occurs when x is 0. And the more that you can do this in your head, not have to rely on your calculator, it's a little bit faster, but you understand it a little bit more, less likely to make mistakes, that kind of thing. But you certainly can use a calculator for something like this. So the cosine of 0 is 1. So that's 2 times 1. The sine, and 2 times 0 is 0, so the sine of 0 is 0. 2 plus 0 is 2. For the x-intercepts, X-intercepts are usually a little bit trickier. We're going to set, whoops. We've done one very similar to this before. What am I going to do to solve this one? All right, so 2 cos x plus 2 cos x sine x. That one's only got one identity, so you have to use that. There's not going to be another way to resolve single angles and double angles in the same question. So if you have a double angle and a single angle, you're going to be using an identity to resolve that. And then we can factor 2 cos x 1 plus sine x. Is that right? Which means cos x is 0 and sine x is -1. And again, these are exact values. Where you can do an exact value, you must do an exact value. So like, this is different from the intercept, because if you punched it into your calculator, you would have gotten the same answer there. That's not what I mean. I mean, you can't do this in your calculator and get a decimal value and use that. In this case, you have to recognize when it's something we can do the exact value of. So where is cosine? Where's the graph equal to 0? Pi by 2 and 3 pi by 2. And where is sine x equal to -1? Here we go. Two of them are the same. I got the same value from two different ones. Does that make, doesn't matter, like that doesn't really tell us anything different. It just happens that way. Okay, so we've got 2 x-intercepts. Everybody okay? All right. I'm going to do all the derivatives here. Again, you can beat me to it if you want. Practice. Derivative of cos is negative sine, so it's -2 sine x. And derivative of sine of 2x is cos of 2x times the derivative of the angle, the derivative of what's inside, which is just 2, so 2 cos 2x. And I'll make the statement here, f prime exists for all x. That way I don't have to worry about it later. You do want to make that statement somewhere just to be thorough. And like I said, I'm going to do all the derivatives here, so I'm going to do the second derivative as well. All right. So we've got our intercepts. I'm going to do the endpoints a little bit later on. I'm going to do the table in a way that kind of summarizes everything, so I've got all the information in one place. So I'm going to worry about the endpoints after. Sometimes some people start with the endpoints and the intercepts and kind of do that first. So we're going to move on to critical values. And they occur when the first derivative doesn't exist or when it's equal to 0. And we've already talked about it exists everywhere, so we're just going to look at where equals 0. What are we going to do with this one? Where are we at? Aleph? Yeah, and how do I know to do that? Well, because there's a sign in it, so I want them to be all signs. Cos 2x has 3 identities, but one of them you're probably never going to use because it's got a cos squared and a sine squared in it. That one probably we don't want, so you're going to switch it to one of the other two, depending on what else is in the equation. So in this case, very nice, I'm going to do negative 2 sine x plus 2 bracket 1 minus 2 sine squared x bracket equals 0. Now I can actually divide through by 2. I don't know exactly what order we want to do all of this in. I'm going to divide through by 2. I'm going to leave the negatives where they are for now, but I think eventually we're going to want to do something to manage the negative. So I'm going to get negative sine x plus that 2's gone plus 1 minus 2 sine squared x equals 0. And I'm going to flip all of the negatives around, so I get 2 sine squared x plus sine x minus 1 equals 0, I think. Does that look right? Did I do everything okay there? And now, what are we going to do? What are we trying to do? We're trying to find the values, like we're trying to solve for x. I think we can factor it. I think it's factorable. You could check the discriminant if you want. The coefficients are positive 2, positive 1, and negative 1, your ABC. So you can still definitely use discriminant. And it's possible that you could end up using a quadratic formula here. Like that is possible. But this one is factorable, I believe. So 2 sine x and sine x 0, and it's going to be 1 and 1, and the 2 is positive, so I believe it's plus and minus. And so I get when sine x equals positive 1/2 and when sine x equals negative 1. And again, both of those we can do exact value. Sine x is 1/2. Don't forget we are in a restricted domain from 0 to 2 pi. Inclusive, which is our standard one, so we just kind of do it the normal way. But so sine x is 1/2, x is, who's good at this stuff? Yeah? Yeah. And 5 pi over 6. Quadrant 1 and quadrant 2, we need them both. And 3 pi over 2, we already saw that one, but that's relevant. That's something we need to think about. There's a lot happening at 3 pi over 2. You can do this now, you can do this later. I want to know what these values are as decimals for when I'm sketching and probably for when I'm doing my table. So pi over 6 is about 0.52, and 5 pi over 6 is about 2.62. So that's really just for my reference for later on. Okay, and finally, points of intersection, no inflection. This is what I mean. You really want to have a strong sense of like how to, like the order and what all of this means and what all the different steps are, because if you were trying to figure this out as you went, there's enough work as it is. They're long questions, lots of work, and you want to just kind of know what to do and go to it. 2 cos x minus 4 sine 2x equals 0. Again, I can divide both sides by -2 in this case. And sine 2x only has one identity, so I'm doing that same thing again. Okay. Factor out the cosec's. Cosec is 0. Didn't we see that somewhere already? So that means x is pi over 2 and 3 pi over 2. There's 3 pi over 2 again. And again, I probably want the decimal values here. So 1.57 and 4.71. And sine x is negative 1/4. What do I have to do with this? Yeah, so x related, if you want to make a note to yourself, it's inverse sine. Oh, this is really important. I think there was another example, but we didn't actually get to it because we ran out of time. And I don't know if we talked about this, but you want to put the positive. I mean, I know you know this from grade 11, but you know it might get lost in all of the mess of all the other stuff that we're doing. You got to put the positive value in, so 0.25. Okay, and that's going to give me approximately 0.2527. And then I'm looking for where sine is negative. There's two quadrants. So quadrant 3 and quadrant 4 angle. And make sure you say that that's x related whenever you do that. And so x works out to approximately 3.3943 and 6.0305. We got 5 minutes, we gotta go. Okay, everybody okay with this so far? This question is so nice. It's got so much going on in it. It's got both of the kind of identities for double angles that we see. It's got a lot of exact value stuff, but then it's also got some non-exact value stuff. All right, let's start our table. X. So I'm going to start at the end point, 0. And then from 0, when I look back at the decimal values, I see that pi by 2 is the first one that I have to consider for the second derivative chart. Pi by 2 less than x less than 3.39. That was one of those values we just did there. 3.39 less than x less than 3 pi by 2, I think. Uh, 6.03. See, like, there's a lot going on here. 2 pi. And then 2 pi just because it's an endpoint. So I'm just having it in my chart. You could do them on the side. I decided to put them in my chart. So y double prime and y. Okay, so I don't care about the second derivative there. It's just an endpoint. Make sure that you know that that's not a negative sign. That's like crossed out. Okay, and that was our y-intercept. We already know that point, 0, 2. I'm going to go through this quickly, picking a value in that interval. This works out to be negative. These ones are all going to be 0. That one we're not worried about. next one, picking a value in here is positive. So pi by 2 and 3.39, I can pick 3. Like pick easy values because of the decimals. We know what pi by 2 is. I've written it down. I can look back at it, but I think 2 is in that interval. 3 is in that interval. Again, you got to practice this a few times so that you get used to doing this yourself. Next one works out to be negative. You could use 4 for that one. I could use 6 for the next one. It works out to be positive. And the last one, 2 pi is like 6.28, right? 2 times 3.14 and 6.03. So I got to use a decimal here. So you could use 6.1 or 6.2, something like that. Make sure that's not the mistake that you make, is picking the wrong decimal value. Okay. The end is 2 pi comma 2. Turns out it's the same as the start, but that doesn't always happen, so be careful of that. There's lots of reasons why that might not happen. This is concave down. This is concave up, concave down, concave up, concave down. Remember the picture we looked at where there were so many changes, so many points of inflection? Same thing's happening here. So this is a point of inflection, point of inflection. And we only have 1 minute left here. So I'm going to start filling in some of these values, and I'm just going to show you quickly. Pi by 2 is an intercept, right? So we know that value. 3 pi by 2 is also an intercept. It is also a horizontal tangent line. It came up everywhere. It came up in the intercepts. It came up when the derivative was 0. That's often a local max or a local min, but this one's not because it's a point of inflection. So there are lots of local maxes and local mins occurring in these intervals. I think there's one in there and one in there in those intervals. But that one turns out to be a horizontal tangent line. So very quickly, I'll have to put the finished graph up, but it does something like this. It goes up, min, point of inflection, and then here, right on the intercept, it does that. And then there's like another point of inflection in here, there's one in here somewhere, or it's actually on the axis there, so there's a lot going on, but this is the one that I wanted to point out. That's something different that happens there. It's really important to be aware of what this is. The first derivative was 0 and the second derivative was 0. That tells us the nature of what's going on at that point. It happens to be an x-intercept as well. That was just the way it worked out. It didn't have to work out that way. Everybody got that? Does that make sense? Okay, so then I would list all of these A, B, C, D, all those points. I'm going to put them all on my chart, A, B, C, D, just so that I can list the A, B, C, Ds there, or you can list them in place. It can be hard to write in all the little points there, but make sure it's clear.